today I'm going to continue the discussion of in a systematic way, the discussion of the structure of perturbation theory. So we just started to discuss the principle being perturbation theory in phi-4 theory, something that you have seen on some examples in previous courses. So I'm going today to discuss its systematics. So perturbation theory. Basically, I'm going to discuss its structure. In the framework, of course, I stay with the phi-4 theory in an Euclidean setting to make things a bit simpler, have no high factor, but that's not important. Once you have understood how to do this, you can do that for any. Okay, so let me remind. We start from the phi-4 theory, which is defined by the action, as usual, the action for a free, massive, free field. We had an interaction which is proportional to phi-4, and we have seen that this corresponds to having a contact repulsive interaction between the quanta of the field, of the free field. And the idea is to make an expansion as a series, which is formal series or asymptotic, and sum over k, gk of the expectation value of operators we are considering. And using Wick theorem, so we end up with, we have to compute expectation value with respect to the free theory of products of operators, some coming from the observable we consider, some coming from the interaction terms, integrated over the position points, and these are some external and internal. Okay, and using Wick theorem, we can express this as integrals over functions of the z's and of the h's that can be written in terms of decomposed in terms of Feynman diagram. So Wick theorem, we get a decomposition, a sum of amplitudes connected to Feynman diagrams or Feynman graphs, two denomination. Okay. And we have seen on the simplest example that of computing just the first term in the partition function of the model, namely z, which is expectation value of exponential of minus g divided by h bar integral d dx phi-4 of x. We have seen in the free theory, so that this is, the first term is 1 plus an amplitude, which is, oh, there is a factorial 4, of course. There is factor g, and there is amplitude associated to a diagram, which is this diagram, where this is the internal point, so you integrate over this point, and you have a symmetry factor, terms that comes from the application of Wick theorem, which is 1/8. And I have not written the h bar factor, but the h bar factor is h bar. Okay, and this diagram, this is the first example of diagram. This diagram means the amplitude associated to this diagram is just integral d dx g of 0 squared, where g of 0 is a propagator of the free field. Okay? So this was the first example. So before going to the systematic, let me discuss the two-point function, because that's explicitly. So I'm going to present the explicit calculation. Yes?
Where exactly does the H bar come from?
The H bar comes from the fact that in the actions there is a G over H bar. And remember, so there is for each vertex, there is a factor G over H bar per vertex. Okay? And the propagator is, well, in momentum space, H bar over P squared plus M squared. Because it's the inverse of the quadratic form associated to the free theory in the functional integral, which has a 1 over H bar. Okay. Well, the H bar, we are not going to play a very important role in the calculation, but they are important at the conceptual level, so I prefer to keep them. They could be set to 1 at each step, but I prefer at that stage to keep them. Okay, so the two-point function, remember, is just in position space given by the expectation value calculated through the functional integral of the products of two fields at two different points, x1 and x2. I'm working in position space, as usual, but that's not important. Okay? And this is for the interacting theory. Okay. So this is the ratio of something, and let me write it again, that will be better. Let me write it again. So this two-point function is expressed in terms of the interacting theory, the ratio of this, phi of x1, phi of x2, times exponential of minus g over h bar times factorial 4 times integral d dx phi 4 of x computed in the equation divided by the partition function. Okay. That's the normalization we need for the interacting theory. This is it. Okay. And therefore, when you perform a perturbative expansion, you have to expand both the numerator and both the denominator. So the denominator, we computed it at first order. The denominator is 1 minus g h bar 1 over 8 times this diagram plus higher order terms. And the numerator is something we have to compute. The numerator is first phi of x1, phi of x2 in the free theory, and then we expand, same game, minus g over h bar 1 over h bar 1 over factorial 4 integral d dx of expectation value of phi of x1, phi of x2, phi 4 of it. I'm sorry. Okay, let me. I just realized that I said in the previous lecture that I'd like to write the external moment, the external position of the point z1. So this is z1, z2, change of notation. Okay, and this is x1 because I just have one x1, but let's write it. Okay. So this is just the free propagator. So the numerator of this first. This is just the free propagator between the point z1 and the point z2. This is of course, and this is expectation value with respect to the free theory. And then you have terms of order G squared. Okay. So Wick theorem states that this can be expressed in terms of contraction. And so let's take this term, just this term, and look at what Wick theorem tells us. So Wick theorem tells us that we have two kinds of contractions. We have the contraction where you have this paired with this, and all the phi 4, you are going to have two pairs, which are going to give us the same diagram than we got for the denominator. So this is going to be phi of x1, z1, I'm sorry, phi of z2, 0 times phi of x1 squared, 0 squared. Okay? And then we have a contraction when we may pair phi of z1 with one of the phi here, phi of z2 with one of the phi here, and the remaining two here. So we are going to have another terms, which is going to be phi of z1, phi of x1, 0, phi of z2, phi of x1, 0, and then the remaining phi of x1 squared, 0. Okay? So, writing this in terms of Feynman diagram, this is just a Feynman diagram where you have the two internal vertices connected by a propagator, and the internal vertex connected to itself. While this second term is more interesting because, well, it's more complicated because there is one propagator connecting z1 to x1. There is a second propagator connecting x1 to z2. Okay, and then there is a propagator connecting x1 to itself. So these are external vertices. So with my convention, I draw them as hollow circles, and this is the internal vertex. Okay? And with these rules, we integrate over the position of the internal vertex. There is an integration here. Okay? So now, of course, you have several contractions that gives rise to the same amplitudes, the same product. So for the first one, there are 3 of them. So there is a factor 3. 3 divided by factorial 4 is the 1/8. Okay? For this one, you have more, because you can choose to connect this one to one of the 4. So for this, you have 8 ways. For this one, you may choose to connect the first one to one of the 4, so you have a factorial 4. No, I'm sorry. Here you had 3, I think. Sorry, 3. The second one to one of the remaining 3. And that's it. Because then you have just a pair of phi of x1 that remains, and you can only connect them in one way. So for this one, you have a factor 4 times 3 divided by 24, which is 1/2. Okay? And in addition, you have the factor minus, so in front of this, you have a factor minus g. And how many h bar do you have? You have 1 h bar, This one was a factor h bar. And this one has a factor. You have 3 h bar because you have 3 propagator, and you have a 1 over h bar because you have 1 vertex, so you get a factor h bar 2. Okay, sorry. And then you are going to have the next term. Okay, so this is the numerator. And remember, the denominator is of this big expression is 1 minus g h bar 1 over 8 times this diagram, integrated over x1. Okay? And remember, so this is a number, this is a number, this is a number, but this number is a product of the propagator times this integral, because the integral factorize. You have that this, the integral over x1 of this is this times the integral over x1 of this. So in some sense, that's a very important rule, a trivial rule. When you have disconnected pieces in a diagram, the integrals, the amplitudes, factorizes. That's something trivial, but easy to see, but that's a very important rule. Which means that if I expand this denominator, which is in G, 1 over 1 minus G something is 1 plus G something plus term over the 1. These terms cancel this term. This is cancelled by this. Okay? Which means that the final result is that the 2-point function in the interacting theory, phi of Z1, phi of Z2, let me call this G2 of Z1, Z2, because it's called green functions, or correlation function. It's given by the following Feynman perturbation theory. First, this is the propagator of the theory, minus G 1 over 12 times the amplitudes of this diagram. We have Z1, we have Z2, and we have Higgs. And this means just the propagator. This represents the propagator, G0 of Z1 minus Z2. And this represents the following amplitudes: integral d dx1, so x1 of G0 of Z1 minus x1, G0 of Z1 minus Z2, or let's say x1 minus Z2, it's not important, times G0 of 0. So these diagrams represent these amplitudes, which is the integral of these products of propagator integrated over the internal vertices. Okay? And you see that in these amplitudes, the vacuum diagram, here has disappeared. It has been cancelled between the numerator and the denominator. It's not present in the perturbative expansion of the green function for the interacting theory. Okay, and in fact, that's this is a general feature. Okay? True at all orders. Okay. So now that you have seen the principle, let me show you, but I think with slides because it would be a bit faster. What are the diagrams that appears for at higher orders and for the higher order correlation functions? So I hope you'll be able to understand what's going on by just if you have understood what I did there, and if not, ask question. Okay, so can you switch on the? Yeah, thank you. Okay. Come down. No. Yes. No. Yes. Yes. Okay. Is it bright enough? Okay. So this is just a reminder of the Wick theorem that we discussed last week, with the set of propagator you get if you compute the product of 4 fields or the product of 6 fields. And if you consider the expectation value of 6 product of 6 fields in the free theory, you get in fact 15 different ways, which are the top 10 by permutations. And now, interacting theory. So when we compute the diagram that appears in the partition function for the free theory, so this is the quantity I wrote. Well, it's hidden down here. This is the diagram that appears at first order in G, in the expansion of G, a vacuum diagram with one vertex. And these are the 3 classes of diagram which appear at second order in G. So there are 2 vertices, K equal 2 internal vertices, that appears when you apply the Wick theorem, when you compute the expectation value in the free theory of a product of 2 phi-4 operators. Okay? And you may contract all the 4 phi together inside here and inside here. Then you get a disconnected diagram made out of 2 diagrams of the previous order. And then you get the new diagram, this one and this one, by connecting 2 or 4 of the 2 vertices together. And if you apply Wick theorem, you count, these are the counting factors that comes out from Wick theorem. 1 over 128 is perhaps a bit small, 1 over 16 and 1 over 48. Okay, so this is for the vacuum diagram. So here are, for instance, the two diagrams which are called connected, because they have only one connected component, and this diagram is disconnected. Okay? So I'm going to discuss a bit later the origin of the combinatorial factor, but for the 2-point diagram that I have, that's just a production of the calculation I did. At order 0 in perturbation theory, we get the 2 propagators. At first order, we get those 2 diagrams. This one is connected, this one is disconnected. But this one disappears when we go to the next order. Okay, so if we continue now, if we want to go to second order when computing the two-point function, we have to apply Wick theorem when we compute the product of 4 operators, 1, 5, 1, 5, 1, 5, 4, 1, 5, 4. And well, with a bit of patience, you get 7 different class of diagram. This one, and this one, and this one, which are connected in the sense that you can draw lines which joins all the vertices, the 2 external vertices and the 2 internal vertices. See? And 4 disconnected diagrams, where part of the diagrams are vacuum diagrams, which are disconnected from the connected part that connects the 2 external vertices. Okay, so you see the logic. And if you don't see exactly how you get this, just think about all the contraction you may build out of, in fact, 10 phi operators, but grouped. Some of the operators are located at the same internal vertices at the same point, which simplifies combinatorics. But of course, when you count the number of ways, at the beginning you have a 1 over factorial 2, which comes from the expansion of the exponential of G phi 4, and the 1 over factorial 4 squared. And then you have to put on the numerator the number of ways applying Wick theorem, the number of ways you construct the same diagrams, which gives a simpler ratio, which is 1 over 4 here, 1 over 4, 1 over 6, 1 over 16, 1 over 100. Well, and here, these are the weights of those diagrams that we got already. So the interesting thing is, here this is 1, 4, this is 1, 4, and here it is 1, 6. So basically, these diagrams are not new. You could have guessed them from what we did in the previous slides. But this one has a new diagram, which appears in the calculation at order 2 of the two-point function, the new connected diagram that couldn't have been guessed from calculation at previous order for the two-point function and the vacuum diagrams. Okay. So now, 4-point diagrams. The 4-point diagrams are a bit more, there is one subtlety. If I'm interested in computing the 4-point function, I have to compute in the interacting theory the expectation value of products of 4 fields. And we have seen that in the free theory, so at order 0, k is the number of internal vertex. So at order 0, in the free theory, it's just given by Wick theorem. So there are 3 different diagrams, which all of them are disconnected already because they are products of propagators, which are 2-point functions. So the 4-point function in the free theory is just a sum of products of 2-point functions. That's Wick theorem. Now, if you go to the first order in the coupling constant, you insert the phi 4 to some internal vertex x1 position, and you integrate over it. And you apply Wick theorem. So now we have to apply Wick theorem with 8 phi operators, 4 of them located at the same point. Okay? And so, first, you may have all this class of diagrams. So here you have, I think, 9 different diagrams, which are basically obtained by, well, making a pairing between 2 external phi, and for the rest of the pairings have to be distributed between 2 external phi and 4 internal phi. So these pairings we are going to reproduce the Feynman diagrams and the amplitudes of the 2-point function. So you see, so if you make pairing between this, and then the remaining, or any of the 2, you get diagram like this, which are products of 1 propagator with connected diagrams of the 2-point function. And of course, you can make a pairing like this, a pairing like this, and then a pairing like that, then you have a diagram with one vacuum diagram and three disconnected parts. Okay, so these diagrams are disconnected and are not new. Now, the interesting point is that this last diagram, this one, which is obtained by pairing the first external phi with one of the internal phi, the second one with one of the internal, the third one, and the fourth one. Because then you get a diagram where you have four propagators. Each of them connects one external vertex to the internal vertex. So this diagram is not connected, is not disconnected. This diagram is connected. See, it's something new. And this diagram, of course, the Feynman integral or the Feynman amplitudes associated to this diagram is just the products of G of Z1 minus 6 times G of Z2 minus 6 times G of Z3 minus 6 times G of Z4 times minus 6 integrated over X. This diagram is something like, if you can see it, this diagram means if I have Z1, Z2, Z3, Z4, the corresponding amplitude is integral over d dx1 of G of Z1 minus x1, G of Z2 minus x1, G of Z3 minus x1, G of Z4 minus x1. So that's a non-trivial integral, which depends on the position of the point Z1, Z2, Z3, and Z4. Okay. Good. Okay. Okay. So now let me discuss a bit what's happening. So what we have seen is that when computing the vacuum diagrams, here are the, well, forget about this one at the moment, which has no internal vertex. These are the connected diagrams of the connected vacuum diagrams. This one, this one, this one. In the two-point function, here are the connected diagrams. And if instead of, and as I stated, in fact, since the two-point function is given by just the ratio of all the diagram that appears here divided by the vacuum diagram, you can check that the two-point function is given just by the sum of the amplitudes of the connected diagram. Okay. So here are the diagrams that appears up to order G squared in the perturbative expansion of the two-point function. Okay. So now, and we start to see some structure, because you see, well, these diagrams are not, we are going to discuss them later, but you see that in the two-point function, the two-point function is made of the connected diagrams, but the connected diagrams, you know, are a chain of more elementary pieces that I have drawn there inside the blue boxes, which are connected by propagators. So you have a line of propagator joining 1 to 2 here, and along this line are grafted some diagrams. So this one, the tadpole diagrams, here you have two tadpole diagrams. Here you have a bubble to which is attached the tadpole diagram, and here we have a diagram with 3 legs. Okay. And what is the property which is shared by these 4 diagrams? So what is the property? Well, let me write it here. Okay. So I consider a diagram that is made out like this one, a diagram which is this one, and a diagram which is made out of this. Okay. So what is the common property of this diagram which is not shared by this big diagram? Well, the property is that if you, well, this one, for instance, this one. So this one, well, let me consider this diagram, for instance. Okay, and compare to these diagrams. The property is that if you cut any, if you remove one edge, one line, if you remove one line, one propagator, it stays, the diagram stays connected. You still have other lines that connect the different diagram. So first, if you remove these lines, these diagrams become this one, which is just one diagram with one vertex, so by definition, it's connected. If you remove this one, what you get is this diagram, which is connected, and if you remove this, you get the diagram which is connected. While here, if you remove this line, then you get this diagram which is disconnected. You cannot join this vertex to this vertex. Okay. So this class of diagram is called one-line irreducible diagrams. Or, in physicist language, one particle irreducible. Okay. Particles, because in physics, you know, to a Feynman diagram, a propagator is usually associated to the propagation of one virtual particles in some intermediate process. And so often you find the acronym 1PI for one particle irreducible. Okay. And you see on this example that this function is made out of a line with propagator joining a string of one particle irreducible part. Okay. Okay, so now let me go back to the 4-point function. So the 4-point function we have seen, these are the diagrams that I draw that appears at order G in the expansion of the 4-point function. And out of these, there is only one irreducible one connected diagram. This cross. All the other ones are disconnected. Okay. So now let's concentrate on the contribution of the connected diagram that appears in the 4-point function. So we remove all disconnected diagrams that appears in the 4-point function, because basically all disconnected diagrams are products of 2 points connected diagram. You see, this diagram is a product of this one by this one is this one by this one, and that's going to continue at next order. So we concentrate on the contribution of the connected diagram to the 4-point function. Yes?
The last two diagrams, you have a loop on one and two legs.
This one?
Yeah, like why don't you draw the other two?
Why didn't I get?
Yeah, like why don't you draw two more diagrams with the loop on 2 and 3?
No, I don't think there's no vertex interval that's the same thing.
No, because this is, I should increase this. This is not a vertex. This is just diagram drawn this is just a diagram drawn in 3-dimensional space. You see, I have a line like this, and I have a line like this. If you prefer, you can write it like this diagram. And here it's clear that it's disconnected. No, I'm sorry. No, I realize that when you are far away. Yes, no, I agree. Okay, I'll have to. No, I'm sorry, I never. No, that's correct. Okay, this is this diagram, yes. Well, these diagrams are drawn in the lecture notes, so look at them. But I have to improve my picture. Good. Okay. So now let me, so I concentrate on the connected diagram. And I go to second order in the perturbative expansion. So I go to connected diagram with 4 external vertices and 2 internal vertices. And then there are more diagrams than just this one, but you have the diagrams where you take this cross and you graft on each of the propagator one of these one loops. You see? So you get this one, this one, this one, and this one. And then you have new diagrams where, like this one, where you have 2 vertices, 2 lines, 2 propagators, 2 pairings between the 2 internal vertices. So you get this one, you get this one, and finally you get this one. Well, those diagrams, these diagrams are just differ by a different labeling on the external vertices. So this one, if you don't see it, you see this diagram is in fact this one, the last diagram. I have one. So this is external vertex 1. This is external vertex 2. I have external vertex 3, and I have external vertex 4. And you see the external vertex 3 is connected to this internal vertex. And this one is connected to this one. So if you prefer, same thing as this one. Okay? Okay. So there are more connected diagram at second order in the coupling constant. But basically, you have 2 kinds of diagram. You have this one, and this one. So you have 2 different, topologically different diagrams, this one and this one. And if you think about whether they can be described by, in terms of those one particle irreducible or those one line irreducible subdiagram, here are the irreducible part. So once again, I have drawn blue circles around the irreducible part. So first, it's a bit of just a mathematical definition. I consider that the single vertex is irreducible, because a vertex is connected, is irreducible if you remove one line, it stays connected. But if you have no lines to remove, it always stays connected. Okay. So this, by definition, this is also irreducible. Take it as a definition. So beyond this simple diagram, you get this one bubble that we already met in the discussion of the 2-point function. And we get this bubble with 4 legs attached, which is also irreducible now. So we have another irreducible diagram, which is this one. This one is irreducible. When you cut one line, it stays connected. Okay. Good. So now let's go a bit faster to the 6-point function. So we have seen that in the 6-point function, in the free theory, there are 15 different diagrams. But if we concentrate on the connected diagrams that contribute to the 6-point function, which are the connected Feynman diagrams that appears in the calculation of the 6-point function, at order 0 in the free theory, there are no connected diagrams. At first order, there are no connected diagrams. Connected diagrams appears only at order 2 in the complete constant. So connected diagrams with 6 external vertices require at least 2 internal vertices. And here is one. It's a double cross. Okay? And the other ones, there are many, many of them, but they are obtained just by, labeling differently the external vertices. So if you make a change between, for instance, 1 and 4, if 4 is here and 1 is here, this is a different amplitudes associated. So it's a different diagram. So there is a bunch of diagrams that are not written here that have the same topology, and they are connected. Okay. Now, if you go to second order, well, I'm sorry, this is second order. So if you go to third order in the coupling constant, so we consider a diagram with 6 external vertices and 3 internal vertices. Once again, you can graph a bubble diagram like that, one of those tadpole diagrams on one of the lines. Okay? Then you can replace one of the internal vertex by this bubble vertex that we met in the 4-point function. There's this one. And finally, we have something which is new. We have a diagram where we have a triangle that connects the 6 external vertices. You see? And of course, those vertices are one particularly reducible part. This is a one particularly reducible part. This is a one particularly reducible part. And this triangle diagram is also irreducible. If you cut one line, it's irreducible. So we get another class of irreducible diagram, which is this one. Okay? Okay. Okay. So basically, this is the logic. You see, there is some structure in perturbation theory. You may correlation functions or Green's function can be expressed in terms of combination of connected diagrams, and connected diagrams are made out of irreducible diagrams, trees of irreducible diagrams. So I can draw this here. The logic that no. The logic is that Green functions, so correlation functions, are made out of connected diagrams, what I'm going to call connected functions. And connected functions are made out of one particular irreducible functions that I'm going to define. Okay? And from the point of view of computing the Feynman integrals or computing, there are much less irreducible functions than correlation functions. Well, there are less diagrams. And basically, all the mathematical information on a correlation function is contained in the irreducible functions. If you know the irreducible function, it's easy to get back to the correlation functions. Yes?
The correlation functions are made of connected,
Yes.
connected diagrams, connected functions.
Yes?
You mean that the disconnected? Because I mean, strictly speaking, there is some disconnected diagrams contained in
Yeah.
the
So,
Green's function,
yes,
but they
no.
can be made out of connected.
Yes, yes. No, what I mean is that, for instance, if you want to compute what is the correlation function, what I call G4 of x1, I'm sorry, z1 up to z4, and if I define G2 of z1 and z2, and if I define the connected function of z1, z4 as just the sum over the connected diagrams of g to the power the number of vertices times the amplitudes, the integral associated, which is a function of z1, z4, then you can show very easily that g4 of z1, z4 is first given by the connected part of z1, z4 plus all the possible combination of two-point functions which are connected, which gives a four-point function. So G2 connected of Z1, Z2 times G2 connected of Z1, Z3, Z4 plus the same thing by taking Z1 and Z3, Z2, Z4, and Z1, Z4, Z2, Z3. So in other words, I can write that a four-point function like this, where this represents the sum over all the diagrams, is just the connected four-point function plus this times this, where this is connected, plus this, well, 1, 2, 3, 4, plus 1, 3, 2, 4, plus the last one. So if you know this, you only have to compute this to get the four-point function. Okay? This is the logic. Okay?
I mean, G2, Z1, Z2 is going to be made up of connected stuff.
Yes.
Yes. I mean, only
yes.
First order. So it seems to depend. The statement seems to depend on what order you're working on.
Yeah. Okay. I'm going to define a bit more formally, but more precisely, what I mean by connected function. So let me, I think, switch off the. Can you switch off the? Okay. Thank you. So let me go back to. Let me go back to this and. Okay, so now I'm going to formalize a bit this. Okay, so let me, it's going to be a bit messy, so, okay, let's start from, okay, so now I'm going to define what are the correlation functions, both general, connected, and irreducible. Okay. So I'm going to define what is the to a Feynman diagram that I'm going to call G comme graph. So G is a graph. I associate an amplitude or a Feynman integral, which is just the integral associated to that. So I'm going to denote it I of G. So I of G depends of its n external vertices. Okay, and this is just given by the integral over the products over the I equal 1 to k, if it has k internal vertices, d dxi times the products over the lines, the propagators, of the propagators g naught of okay, and this may be a z or a x, depending of whether this is an external line or an internal line. Okay, so you see what it means. So this is okay. Now, to each diagram, we have also a symmetry factor, which I call C of G, which was this factor 1/2, 1/8, etc., that we, which is basically the number of ways to construct G, the diagram G, out of Fick theorem, divided by the factor that we had on in the perturbative expansion, which was factorial k times factorial 4 to the power k, because there was a 1 over factorial 4 per internal vertex, and there was a 1 over k that comes from the exponential. Okay, so this is a rational number, but in fact, one can show that this is something which is 1 over the number of elements of the symmetry group of G. So to each diagram in graph theory, you can associate a symmetry group, which is the way you can change labelings of the edges, the propagators, and the vertices. And some diagrams have some symmetry. For instance, this diagram has a symmetry when you exchange the two lines. So it has a symmetry factor 2, hence the factor 1/2. So I don't think I have time to discuss that in more details. We can come back later if you like. And this is explained in more details in the lecture notes. And you can find the explanation in many, many textbooks. But basically, this C of G, this coefficient C of G, is you don't need to apply Fick theorem each time that you want to see. You can, if you, with a bit of training, when you have a look at a diagram, you can deduce directly its symmetry factor. Anyway, so there is a 1 over 3, okay? And with this definition, you see, with this definition, what I'm calling correlation functions with endpoints is just, I'm going for Gn of Z1, Zn in the interacting C. This is the sum of a k, in general from 0 to infinity. There is going to be a factor minus g to the power k. And then there is going to be the sum of Feynman diagrams with n external vertices and k internal vertices times this symmetry factor associated to graph G, so times the amplitudes associated to this graph. So by definition, the correlation function, take it as defined in perturbation theory as a formal power series in G of the amplitude associated to all the possible diagrams. So that's what perturbation theory tells us. Okay. So now, this is the definition for the correlation function. Then we can consider what I'm going to call the connected correlation function. So the connected correlation function is going to be exactly the same thing, except that I consider only the connected diagram. So I'm going to call something that I want to call Gn connected of Z1, Zn is given by exactly the same formula, sum over k minus g to the power k times sum over diagrams G, but the diagrams are connected. Okay, times C of G times Ig of Z1, Zn. Okay? So take this as a definition. Okay? And finally, I'm going to define an object which is a bit more subtle. So I think I should use another blackboard. Okay, well, let me go back to this one. I'm going to define what's called, so this is first correlation function, two connected correlation functions, and third, so correlation connected. I'm going to define what's called an irreducible function. So I want to associate to any irreducible diagrams like this, an amplitude. Okay, but there is, so here is an irreducible diagram. You must think about what is called an one particle irreducible diagram. You must think of it as a diagram like this one, which is a part of a Feynman diagram, but with some of its propagators are external to the irreducible part. So you must think of an irreducible diagrams as a Feynman diagram that appears in the phi-4 theory, but with some external legs which are outside, you see. So these legs are called external, or rather truncated legs. That's the denomination, you see. And then you have inside, you have internal legs and vertices. Okay. So again, an irreducible graph has external vertices up to the n. It has internal vertices. Okay. But I'm going to define what is so far one particle irreducible graph. Let me call it again G, defined in this way. I'm going to define its amplitudes, I irreducible of G, of Z1, Zn, in a slightly different way. I'm going to define it as, by this definition, a big integral products over the internal vertices labeled by I from 1 to k of dxi. I'm going to associate to the internal lines the propagators, products over the internal lines G naught of x from x, because the internal lines joins internal vertices to internal vertices. So for instance, let's consider this diagram. See, these diagrams has two external lines, 4 external lines, Z1, Z2, Z3, Z4, and 2 internal lines. So I have G of x1 minus x2 squared for this diagram. But then, for the external lines, or truncated, I don't want them to play a role in the amplitudes because they are in the tree. So I just introduce a delta function of z and x. You see. So you see, in this, the perturbation rules is that it just enforces that z is equal to x. Because this removes the effect. Okay. So the rules is that, pardon? Yeah, there are some labels, but simply it depends on the labels here too. So for instance, you see, the rules is that this is a propagator, 1 over p squared plus m squared, if you like. And for an external line, or truncated line, I can also, usually it's drawn by just cutting them like that. This is the Fourier transform of delta, which is 1. So in Fourier transform. Okay. So for instance, what is the amplitude associated to this diagram? It's just integral dx1 ddx2 times g0 of x1 minus x2 squared, the propagator, the 2 propagators, times a delta function of z1 minus x1, delta of z2 minus x1, delta of z3 minus x2, delta of z4 minus x2. Okay? So then, in this particular case, you can integrate. So this is the amplitudes of the irreducible diagram associated to this diagram. It's a function of z1, z4, of the 4 z's. This is just, if you integrate over x1, you get that x1 has to be equal to z1, but also has to be equal to z2. So what you get is just a delta function of z1 minus z2. Similarly, integrating over x2, you get a delta function of z3 minus z4. Okay? And then you get g naught of z1 minus z3 squared. So you see. So the amplitude of this irreducible diagram here is just products of delta functions times the products of two propagators associated. So these 2 points have to be there, and these 2 points have to be there. You see? So this is a representation of this diagram in position space. And if you want to go to momentum space, and let me, well, I'll draw that later, because let me just draw that. You are going to have a function of momentum. Okay, so this is a definition of the amplitudes associated to an irreducible diagram. Yes?
So if the points at the end of the external legs were internal rather than external points, would you define it the same way?
If the points here?
Like the Z1 through Zn?
Yeah.
Like they can be internal points in your big diagram and so on.
Yes, yes. No, they may very well be internal points. But I'm just considering what is the amplitude I associate to an irreducible part of a big diagram. So I consider all the other points in the diagram fixed. It's just that's something that will play the role in some intermediate calculation of the amplitudes. Now. Okay. And then, so once we have done that, we can define an object which is an irreducible function. The endpoint irreducible function that I'm going to call gamma n, which depends on endpoint z1, zn. It's defined exactly in the same way. It's defined as the sum of a k. I'm going to have a factor g to the power k with one subtle definition. I'm going to have minus 1 times minus 1. Well, I'm going to have minus 1 to the power k minus 1 times g to the power k. This is a technical difficulty. Times the sum over the irreducible diagram, one particle irreducible graphs. Of course, with n external vertices and k internal vertices. So with this definition, so this is an irreducible diagram with 4 external vertices and 2 internal vertices, because it has 4 truncated legs, times, well, the symmetry factor associated to this diagram, times the irreducible amplitudes, okay. So take this as a definition. Okay. The reducible function is called gamma. Okay. And this works for everything except, and that's an important point, except for the two-point function. So you may ask, what is the irreducible two-point function? What is the okay, so what I'm going to call gamma 2 of Z1, Z2. Okay, so it's going to be the sum of the irreducible diagram. So what is the irreducible diagram? There is an irreducible diagram which is just obtained by this one. We had this diagram which was with those two legs are truncated. And we get a factor, so it has one internal vertex, so there is a factor. So there is a factor G, and there is a factor 1/2, which is a symmetry factor. Okay? And then at order G squared, we get a minus G squared, and this and this are the irreducible diagram that we get. So we get minus G squared, and we get this diagram with a factor 1/8, and this diagram, which is irreducible, which has a factor 1/6. And I'm not mistaken, okay? Okay? And the amplitudes associated as this to this irreducible diagram is just delta of Z1 minus Z2 times this. So this amplitude is delta of Z1 minus Z2 times G of 0. This is delta of Z1 minus Z2 times integral over x of G of x squared times G of 0 for this diagram. And for this diagram, this is G0 of Z1 minus Z2 to the power 3. Okay? Okay. Okay. But so now there is a little subtlety. In the connected one-point function, we had this propagator. Okay. Can we define an irreducible propagator, which is obtained by this propagator, but removing it twice, because we have to replace this propagator by 1 or by delta function at each extremity of the point. You see? Okay. So take as a definition, so we have somewhere here an object which is the twice truncated propagator. Okay, and it has to be defined properly. Okay, so in order for this to be consistent, what we have to do is that, remember, in position space, the truncated propagators means that you take the ordinary propagators and you replace it by 1. How do you replace a propagator by 1? You replace it by applying this operator, the inverse of the operator, and you get 1. So if you want to be just self-consistent, if you want to apply, to truncate it twice, you apply, and 1 is just delta, I'm sorry, 1 is delta of Z1 minus Z2. Oh, this is the operator identity. So you apply it twice. So what you get is a distribution. Which is a distribution. Okay. And in Fourier space, the Fourier transform of this is 1, while the Fourier transform of this is p squared plus m squared, where p is the momentum carried by the propagator. Okay. So in Fourier space, the first term is the distribution minus Laplacian plus m squared applied to the delta distribution. But in momentum space, so this is in momentum space, and if you work in momentum space by Fourier transform, this gamma 2 of Z1 and Z2, this is just going to be, well, the Fourier transform is a function of P, the momentum, so you have something with the momentum that's flowing on. This is going to be P squared plus m squared. This is going to be G 1/2 times the Fourier transform of this is 1. So you get just G0 of 0. This is minus G squared times 1/8 times this object. Okay, which is independent of P, of the momentum P. And this is this object, which, if you have an incoming momentum, is some function of P, which is non-trivial, because it is the Fourier transform of the square of the propagator. And the propagator in momentum's case is 1/p squared plus m squared. So it's a convolution of 3 propagators. The Fourier transform of the product of 3 non-trivial functions of p squared plus m squared. So this is a function of p which is interesting and non-trivial. Okay. So now I just have, well, I can use, I think I can use my last blackboard. Okay, so we have defined some formal objects which are basically the sum of the amplitudes associated to diagrams, connected diagrams, and irreducible diagrams. Okay, and they contain the information we need for physics. So now we are going to define what are generating functions. And I will end up here these lectures. So I already introduced generating function in the term of correlation function, remember. I defined a function z of g, which was just a functional integral of a phi exponential of minus 1/h bar the action of phi minus g dot phi, where g is a function, this is a source term, and g dot phi means integral d dx, g of x times phi of x. Okay? So this is a functional, of the source term g, source function. Okay. And So this object is in fact the generating function. G is a generating function associated to correlation functions. Because, as we have seen, if we consider the functional derivative of G with respect to G, we get some phi. So in other words, we can expand in G. That's something. Expand in G, Z of G. And we get the correlation function. So we can write that, for instance, that, well, one easy thing to do is to write that Z of G divided by Z of 0, which is the partition function. Z of 0 means G at G equals 0. It's just a sum from n equals 0 to infinity of h bar to the power minus n divided by factorial n. I'm expanding in G, the exponential G. And then we have a big integral products from A equal 1 to n of d of ZA, G of ZA, times the correlation function Gn of Z1 up to Zn. So you see, this object, this function of Z, contains all the information, or all the green functions. You see, it's a formal sum, but it's a series in G that contains all the correlation functions. Okay. Good. So now, and we have, you see, we have two definitions here. We have a functional integral definition, and we have a diagrammatic representation, and they are equivalent. You see, so this is a diagrammatic form. Diagrammatic. And here we have a functional integral definition, okay, of the same objects. Okay. So now you can do the same thing. You can define a generating function for the connected correlation. Okay? And I'm going to define here in a simple way. I'm going to define it here as W of G. Well, technically it's often called W, because W comes before Z, but okay. And I'm going to define it exactly in the same way as a formal series of sum from n equals 0 to infinity. I'm going to have an h bar to the power minus n, but for technical reason, I'm going to have an h bar 1 minus n divided by factorial n. And then I integrate for each term over the n. I integrate over all the possible positions of the external points of ZA, G of ZA. So this is a polynomial of degree n in the Z's, because there is one G per A. And then I replace simply the complete correlation function by the connected correlation function. Okay? So this is a diagrammatic definition. Okay? The question is there a similar path integral definition for this one? Okay. And the answer is yes. And the answer is very simple. That's something that probably you have met in statistical mechanics. W of G is just h bar times the logarithm of the generating functional for the correlation function. So this is a functional integral as well as combinatoric. W of G is just the logarithm or Z, or equivalently, Z is just the exponential of W of G divided by H bar. Okay. Okay, so let me end up the lecture here, and tomorrow I'm going to show you, well, briefly, what is the functional integral definition of the generating function for the irreducible two-point function. And that's something that is important, both for physics, because those irreducible functions plays an important role in physics. The generating functional is called the quantum effective action. And there is a beautiful relation between W and the generating function for the irreducible function, which is through what's called the Legendre transformation, which is something that is met often in physics, especially also in statistical mechanics. So tomorrow, same thing for irreducible. And then we'll be in a good position to discuss ultraviolet divergences and renormalization, because they are discussed in a very clean way and easy way dealing with the irreducible functions. Okay? Good. Thank you.